Hello everyone, and thank you for joining to this session. Also, I'd like to thank you for giving us the chance to speak here today. My name is Hideki Sugimoto, CTO NSITEXE. Today, we will talk about mainly vector extension and its compliance test, but before I enter to the detail, I'll talk about our understanding of the RISC-V architecture and our vision. So let's start. First section is about our understanding of the RISC-V, especially what is value. Why RISC-V? I think there are the three major reasons. First, there are many features to support today's new innovative applications. I'll show later, but we are in the automotive industry, so of course automated driving is one of the major interests as a new application. So secondary, same as other embedded system, it requires very efficient implementation and limited power or thermal condition and sometimes cost. Finally, as you know, ecosystem is quite important to support complex and high quality system development within limited design time. My major experience is processor architect over 25 years, so I know many examples that the history of the either instruction set architecture constrains itself. RISC-V either is much more modern definition and still have enough space for extension. Now, binary level compatibility is not important today, so it is good timing to define a new either for new generation processors. RISC-V is already supported by many members from wide application area. It will be good to keep flexibility, scalability, and wide coverage of the applications, I mean the more generic. I'll end of this section with introducing current implementation of the autonomous driving system and its issue. We are already using many types of processors or the logics to support whole AD system and limited power, thermal, and cost budget. Each element has a reasonable efficiency, but it is not easy to implement, especially how to care the matching between the software and the hardware characteristics. And of course, generic difficulty of the heterogeneous compute is also our issue. To resolve this issue, I believe the either extension is useful to reduce the variation and the number of processors elements. And of course, generic difficulty of the heterogeneous compute is also our issue. To resolve these issues, I believe the either extension is useful to reduce the variation and the number of processor elements. For example, vector extension can support light AI or vision and a related process, and it means main AI engine can be optimized to large context and high throughput workload, which requires quite different characteristics from light one. Now, I will introduce about our vision, including a very brief company information. NSITEXE is subsidiary of Denso, automotive components company. We start to operate from the 2017, so younger than RISC-V. Our major product is processor IP, which can innovate embedded system architecture more flexible and scalable. We already released multi-thread parallel processor called DR1000C, which based on the RISC-V architecture with vector extension. Explain more detail later. It is targeted to real-time control area like a powertrain ECU. We start from the low end because usually low-end embedded system has more restricted requirements, and to have a good scalability, These requirements should be cared from the initial time of processor design. Now we are working to extend to high-end, which is targeted larger dataset-based system, I mean edge computing, including the AD generation vehicle electronics. Today, I'll not jump into detail, but this chart shows our understanding of the AD system. As I explained, we are using many types of processors, but in some area we cannot find efficient one, and using the specific hardware logics. Sorry, this chart only shows the image of the characteristics because it's too complex to show in reality. But the left-hand side is sensor side, usually well parallelized with static and symmetric flow. And right-hand side is decision and actuation side, usually more complex, dynamic, and sometimes a sequential flow. Intermediate part is combination of these, and that's a major reason that the existing processor is not fit to this area. As I said, RISC-V has good capability of extension, and again, that is one of the big reasons with choosing RISC-V. Finally, we hope we can have more generic, flexible, and scalable SoC which can support innovation of system or the software by avoiding too strong relation between system, software, and hardware. Now I'll switch to Adachi-san, lead architect of our processor.
Hello everyone, my name is Koji Adachi, NSITEXE. From here, let me explain our DFP detail and Impellers Vector Compliance Test Suite, which is used for DFP vector unit verifications. CTO Sugimoto explains the target of DFP. DFP has a slightly unique architecture that adopts RISC-V ISS to achieve this target. As the first big picture, DFP architecture is a MIMD style rather than SIMD. We have chosen the multi-core and multi-threading architecture with a large number of threads and hearts in processor complex. Because we intend DFP will be applied in a variety of embedded applications. We have also adopted the RISC-V vector specs. It targets to increase the computing performance. Our vector unit is optimized by sharing the configuration with the multiple thread. The reason why vector unit is shared by multiple thread. In our observations for the customer code, actual customer applications doesn't have enough parallelism to utilize vectorization because there is some serialized part. This serialization will spoil vector unit because it causes vector unit will be idling. To avoid this waste, DFP's scalar unit shares the vector unit and issues the instructions by interleaved manner. For the software stacks, currently we want to use the standard RISC-V tool for the software stacks, but we also would like to contribute to LLV and backend. So we are planning. This is a feature list of the DFP first product, which called DR1000. The DR1000 consists of 4 scalar units, which shares a single vector unit. And there is one housekeeping core, which manages thread scheduling. The vector unit is configured in 5 12-bit wide configurations, and it has large register files. In more larger configurations, the units in this set are clustered together. The DR1000 targets automotive control area, So it provides hardware redundancy features to meet the automotive HUD functional safety standard. Specifically, all SRAMs are protected by ECC and the core important parts are protected by lockstep mechanism. Here is a DR1000 performance comparison graphs when compared to a typical single-issue Scala cores. Regarding arithmetic resources, DFP has only 16 times more resources than Scala cores. It means 512 bit. But due to the large amount of register files and shared vector resource mechanisms, it can realize DFP performance can be exceeding 6 times higher than Scala cores. For the efficiencies, as an example, vector unit can achieve over 90% utilizations when executing the matrix-matrix multiplication functions, which called SGEMs. We can observe high efficiency in DFP architectures. To talk about verifications, let's look at the instruction set of DFP. DR1000 is designed as an accelerator for arithmetic computations, not as a host CPU. So it has a typical but small configuration set which describes in this table. Scala part follows the RISC-V ratified spec, and they are verified by the RISC-V compliance test. Vector part also follows the RISC-V vector specs, but in our development, we choose RISC-V vector version 0.8 draft version with some our tailorings. In the beginning of our development, there were no simulator and no testings. So we have verified our design by the own verification item that is made by ourselves. In other words, there was no third-party verification for vector unit. This is the DR1000 vector configurations. The DR1000 only adopts a limited vector specification to specialize in automotive target applications. Currently, to expand the DFP area, I'm also planning to support complete vector specs in our future products. But even in current limited specs, RISC-V spec is very large and it has too wide diversity to verify completely without any third-party helps. Finally, I explain the DR1000 verification schemes. Thanks to RISC-V ecosystems, we have easily developed our own design verifications flow. We are using RISC-V tests, compliance, etc. And also our own other formal methods are used. However, the piece of vector spec verification was still missing until we asked Impellers. I will now discuss the Impellers Vector Compliance Test Suite to cover these gaps. Of course, Impellers Vector Test Suite is developed by Impellers, but I will be speaking on behalf of Impellers. Impellers Vector Compliance Test Suite has been developed in accordance with the various manner of the RISC-V Compliance Test Suite. The RISC-V vector specification has a large number of combinations, and it's very difficult to create the complete set of the test pattern. But the configurator, which is developed by Impellers, this generator will generate the patterns based on the specs to be tested. The generated test coverage targets are equivalent to the existing RISC-V Compliance Test Suite. In fact, NSITEXE just submit our specifications to Impellers with a simple template. Then, we had the desired test vectors from Impellers. This is a standard component of the Impellers test suite. The component includes the Impellers reference simulator in addition to the various files which needed to run the RISC-V Compliance Suite. The test is provided as an assembler source, and the user requires a GCC and linker script to run in the target environment. The test process begins with the test assembly, followed by the simulation on the ISS, recording of the output signature, execution on the target device, and signature comparisons. This process is repeated for each test. I've talked about the Impellers reference simulator in previous slide, so here is a quick look at it. This simulator is already well known to people involved in RISC-V development. It is an industrial quality reference model. I also usually use it when I want to confirm the behavior of RISC-V specs. I think it is an easy way. My colleagues also use it for the software development. As a recent news for this simulator, the feature to measure the functional coverage of instruction is added. For further information, please see the link below. Here is a more specific example of the vector compliance test. Test suites are split into several directories, one for each category. VB means the base instructions. VF means the floating point arithmetics. VI means the integer arithmetics. VP means the vector permutations. VR means the vector reductions. Vx means the fixed point arithmetics. Each directory has a test for each instructions, for each SEW, for each LMAR, and without masks. Let's take a closer look at the fixed point categories. In the fixed point categories, there are 600 test source files. In these test files, there are 28 different instructions and 700 kilo total instructions. By this fixed point category test, total cover group has reached to 93%. Impellers Vector Compliance Test Suite provides this kind of test to users. In the remaining slide, let's look at the actual compliance test flow for study. This is a graphical representation of what I have already described. Here is assembler test, compiling the assembler test, then we get the ELF file. The ELF file is the simulator input. The simulator generates the signature. The generated signature will be compared with the DUT. Next slide shows the internal structure of test code. I think there is nothing special. Very typical test program structures. This is a command line option example for Impellers reference simulator. You can see the option to specify vector configurations. Blue-colored lines are useful command line options to understand the structure of test case. Next slide shows the example trace output. With these command line options, the load instruction for the precondition load looks like this. I think in this case, the vector length is very long and the logs seems float like this. This is the trace output after executing the VAT instruction. you can see the result of V-AT instructions. Impellers reference simulator has some more useful features, such as indicating instruction change point. This is a test list of the test V-AT instructions. These kind of lists are also provided to users by Impellers. Finally, let's take a look at the result of applying the test case to actual our design DR1000. The Impellers Vector Compliance Test was applied later in the verification phase. Despite the fact the design was about 90% verified by our own test items, but we were able to find the two additional issues regarding vector specification understandings. We did not detect any hardware implementation issue, but this is the expected result. For the hardware implementation issues, we should use other method, RISC-V DV or directed test or other static test. Anyway, Impellers Vector Compliance Test Suite has been used for commercial level product verifications. I think this is a good example and test case to show the capability and effectiveness of Impellers Vector Compliance Test Suite. Here is a video clip from Impellers CEO Simon.
Hello, my name is Simon David. I'm the CEO of Imperas. I've been involved in the compliance task group for the last 3 years. And in that group, we've been focusing on the unprivileged parts of the RISC-V ISA, the RV3264 IMC, and we've been developing test suites and a framework for those. And most recently, our focus has been around the formal model and to ensure that that works within the framework as well. We haven't spent a lot of time on the privilege mode, interrupts, exceptions, and we haven't yet looked at things like the new extensions like the vector bit manipulation and things like that. As Imperas, what we've done is we've focused on our simulation technology, riscvOVPsim, which we've made available to the compliance group. And it does have all the behaviors for the vectors and bit manipulation, and it models those and is a reference for those. And we've also, with Imperas, been developing compliance suites for these new extensions. Our Imperas Vector Compliance Test Suite was initially developed for a customer under contract, and it was to ensure that that customer's design was correct to the ISA standard as it developed. And since then, we've developed it a lot. We've used the Imperas Directed Test Generator, which can be configured for specific ISA versions. So for our test suite for vectors could be 0.8, 0.9, 1.0 draft, etc. And also for specific vector engine configurations, for example, the SLEN, VLEN, ELEN, and other customer-specific implementation choices. Generates a reference signature. They're validated with the reference simulator riscvOVPsim from Imperas. Customers can then use those references or the reference simulator to validate their RTL in a normal hardware verification methodology. Vector compliance suites are currently delivered as closed source because they're configured for specific customers' requirements and designs. But it is expected that over time, these will be open source. There'll be open source versions of the compliance test suite configured for common configurations.
Thank you, Adachi-san, and a valuable message from Simon. Now I have summarized the session. First, RISC-V and its vector extension is a great solution for many applications. Second, we NSITEXE will produce several processors based on the RISC-V architecture with some extensions. And third, compliance tests are important to control compatibility of architecture. Then Impellers solution has great opportunity for all designers, and we already catch some incompatibility using this solution. Finally, we NSITEXE will continue to improve the RISC-V based design and want to contribute our achievements. Thank you all for listening. It was a pleasure being here today. If you have time, please join the following Q&A session. And also thank you to Impellers for a great solution and support. Well, that's it from us. Again, thank you very much.